Welcome to Study Loop.
Okay, we have got an NMR spectrum for cinnamic acid. What does cinnamic acid look like? And what we can do is assign each of these signals to a proton in cinnamic acid. So what may be good is to draw in protons here. And if possible, let us group them, right? Because we have some symmetry here, which means that these two protons will share a signal, and these two protons will share a signal, right? Because they are chemically equivalent, which is also represented by the fact that we could rotate freely about that bond, meaning that these hydrogens aren't spatially unique. They could easily take each other's places by rotating about that bond. Okay, so let's just go ahead and give these letters. Let's call this HA. Let's call this B, C, and then both of these will be D. This will be E. This will also be E, and this will be F. Okay, so we see right away that we have 6 protons, which is good because if we look at our spectrum, we see that the total integration value of each of the signals, the total of the integrations is 6, which is what we would expect for cinnamic acid, having sorry, the total integration value is not 6. It's sorry, we have 6 signals, which corresponds to having 6 protons, and then the total integration value should be 1, 2, 3, 4, 5, 6, 7, 8. And we do find that we have signals going from 1 plus 1 is 2, plus 2 is 4, plus 3 is 7, plus 1 is 8, right? The total integration values, when we look at the values, for example, if we look at the rightmost peak, we see they have this 1.00. That means that this corresponds to a single proton, right? And so the signal that is a little messier, that's in between 7.4 and 7.5, they say 3.00. That means that there's a total of 3 protons located in this signal, right? And the sum of all of these totals up to 9. Okay, so let's continue onward. Okay, the first thing that we can do is we can assign this proton, right, to the leftmost peak at 12.19. And that's on the basis of chemical shifts for hydrogens and carboxylic acids are in the range of 12 and higher. Okay, so that's how we get this one assigned. Okay, the next one that we could do would be something like HB. How can we do that? Well, HB, we'll notice, is not aromatic. It's not on our benzene ring. Okay, and while it is next to a carbonyl and participating in a double bond, its chemical shift we should expect to be the least deshielded compared to all of the phenyl or benzyl locations on the ring, right? So based on chemical shift, we should expect this to be the peak at 6.5. We'll also notice that the peak at 6.5 is a doublet, right? Which we would expect given that HB has a single neighbor, right? HC. HB neighbors HC, so HB and HC split each other, right? We also may notice that this splitting is the J value is 6.49 minus 6.47, right? So that's 0.02. Okay, and that's in ppm. If they told us what this is, a 600 megahertz machine, so we could, in fact, say that the value in hertz is simply going to be the splitting constant in ppm multiplied by the 600 megahertz that the machine is operating at, which is meaning that the J value in hertz is 12. Okay, and a J value of 12 is commensurate with 2 protons, which are trans across a double bond. These splitting values are usually in the range of 12 hertz. Okay, so that's another evidence that the peak at 6.5 is proton B. Not so bad. Okay. Now we've got a little bit of a messy situation at as we look between 7.9 and 7.4. Okay, 8, 7, 6, 5. Okay, and we notice that in between 7.4 and 7.5, we've got a messy multiplet that integrates to 3. Okay, and then at in between 7.5 and 7.6, we've got another multiplet that we can't really identify that integrates to 2. And then at 7.8, we've got a pretty clean doublet, which integrates to 1. Okay. And we'll note at this point what we have left unidentified on our molecule is HC, our HDs, our HEs, and our HF. Okay, and things are going to get a little harder to precisely pin down here, but we may notice something going on here. For one, is that all of the splitting is going to get really hard to identify here because they're giving us these splitting values, like for example, between the peaks in this multiplet are reported as 7.42, right? Which is to say that in hertz, all of the splitting is, or in ppm, if we do 7.42 minus 7.42, we're going to get 0, right? So like they've, by not converting the units, they're not actually telling us what the splitting constants are. We can't derive J values from this, other than to say that we know that the difference in ppm being less than 0.01, which if we multiply by 600 tells us that the ppm's difference is less than 6 hertz, right? So all of these peaks must be closer to each other than 6 hertz, which is, worth noting. Okay. So any splitting going on there is within 6 hertz of each other. That's not true for over here, right? So we see that this is a doublet of doublets, right? And that there is, if we go from, say, 7.57 to 7.56, right, we do get a 0.01 ppm difference, or a splitting constant of 6 hertz, right? But then within those doublets, so it's like a doublet of doublets, in which one of the splitting values is around 6 hertz and the other is smaller than 6 hertz. We know for certain, right? So do any of these look like they could be doublets of doublets? Yeah, E looks like it could be a doublet of doublets, right? We've got, 2 neighbors that are technically different. So we might expect a triplet, or we may expect a doublet of doublets, right? Furthermore, we'll note that, hey, E, right, there's 2 of them, and this integrates to 2, right? So this peak at 7.565, right, just taking 7.57 plus 7.56 and divided by 2, which will give us the central location of our doublet of doublets, seems pretty reasonable, right? Okay. Next, we can look at maybe this peak and sort this out. Here we've got a single proton, and we'll note that there's a splitting constant of 7.84 minus 7.81, right? Which would imply 18 hertz. Okay, so it's very likely that the J value is 18 hertz, being a difference of 0.003 ppm. Now, due to rounding, it's very likely that this is just a rounded up version of this 12 hertz splitting constant, right? Typically, that's 18 hertz is far too large for any splitting constant we should expect to be reasonable, so it's much more likely that perhaps that the true value of this is like 14 hertz, and it was rounded down to 12 here and rounded up to 18 here. So, this is just a limitation of the few digits, significant figures they gave us, which isn't helping. But if anything is more than likely to be paired, it's going to be this 12 and the 18. Right, because anything else is so close as to the splitting values are so small as to be indistinguishable, where these two are both large enough to have given us multiples of 600 ppm or hertz that are closer to each other than anything else. So it's most likely then that this peak, which is centered at 7.8125, would be for HC. So let's recap what we've gotten so far. Okay, so E, we expect to be the peak at 7.565. Okay, C, we expect to be the peak at 7.825. B, we expect to be the peak at 7.48. Okay, and then A, we expect to be the peak at 12.19. We know B and C talk to each other with a splitting value that is between 12 and 18 hertz. We can't say for certain. And then what remains is 3 protons which overlap each other: HF, HD, and HD, right? And these 3 are more than likely represented by the peak centered at 7.42, right? Which amounted to 3 protons. And we can't tease those out because we have no way of zooming in further on the integration or on the peaks of the NMR. Okay, so we've at least assigned the peaks to their chemical shifts and reasoned about the splitting constants and the splitting patterns as much as we can, given that they gave us the splitting constants in ppm, which are so closely spaced together to destroy any kind of non-extreme splitting values like being 12 to 18.